can also help us, excuse me, when we think about robots. So, a robot has sensors that, like cameras and all that, and it measures things. So there might be a proximity sensor, there might be a sonar, many sensors, and they give measurements in a given time sequence, time slice. So, for example, a proximity sensor gives you sensing output once a millisecond or something like that. So there's one measurement at a time. It measures now, how about now, how about now, how about now, right? So sensors increase the robot's knowledge, and we're gonna talk about sensors as the letter Z, and there can be many sensors. And we're gonna talk about the letter Z, where there's sensors from time 1 to time n, right? So first sensing, second sensing output, third sensing output, and so on until the robot stops. Now, we also have control data. These are the robots, what's called the actuators, which are basically a hand if the robot has one. Sometimes it could be the wheel, but any action done by the actuators changes the state in the environment. For example, if you change the speed, you will change your position at a given time slice, at a given time frame, right? Now, every time we sense, we gain knowledge about the world because we can see, right? Think of a human. If you open your eyes and you're able to see, or if you're able to hear, if you're able to touch, you increase your knowledge of the world. Now, when the robot moves or moves the arm or changes speed, it induces a loss of knowledge about the environment. Again, think of the human. If you only rely on tactile input, when you touch something, it increases your knowledge about that. And let's say now you move that to the right. You're not sure what the world is now. Maybe you just uncover a door and a monster's going to come eat you. I don't know. There's more uncertainty. Every time you act, there's a little bit less that you know about the world, and every time you sense, there's a little bit more that you know about the world. And robots have to combine those two things all the time. So let's assume that there's one measurement at a time in the sensors, for example. And also, let's assume the following. Again, a Markov assumption, which is to think that the current state of the world, so the way the world is at this point in time, depends on the way it was previously, and everything that you've sensed till now tells you a little bit about it, and also every action you've done from the beginning till now tells you a little bit about the current state as well. So basically, the current state depends on all previous states, all previous sensor controls, and all previous actions that you took. So now, if we only think about it in Markovian ways, if you will, okay, let's think about it in Markovian logic. We can think that the current state depends only on the previous state measurements and controls. So we're going to say this to simplify the model, and it actually works pretty well in practice, is to say that the current state depends only on, we're going to make it depend only on the previous state. So we're going to say that the model will just be simplified to the state depending on the previous state and the actions that I did to change that state, okay? And my measurements will depend only on the state of the world. Let's explain this because these are two different probabilities of measurement, right? So let's say that xt is a complete state. So for example, the room that I'm in, or the way there's a box configurations are in the room, or the way that some room is configured, right? Let's say that if you move a box in this room, or if you change your position, right? Now the state has changed. If you were looking directly into a box, now you're not looking directly into a box, and whatever you're looking at is, a different state. But you don't need to know everything you've looked at to know what the state is right now. We're going to assume in this little world of us, we're going to assume that the state of the world right now, so whatever it is that you have in front of you, let's say that that's the state of the world, only depends on what you had previously and what you did. So for example, if you previously had a box and you moved one wheel of the robot at a certain speed, that made the robot spin and the state changed. The change of states does not depend on what you sense. What you sense depends on the state. So for example, if there are no boxes in front of me anymore, my sensors are not going to report anything. If there's a box in front of me, my sensor is going to report a box. So the state of the world influences the sensor. So this is what this means. The state of the world influences a sensor with a certain probability in time slice t. What this one here means that the previous state and the actions that I took in the next time slice influence the state at that same time slice. Again, if there was a box in front of me and I move to the right, there's a probability of that there will be or won't be a box, right? Now, if there's a box in front of me, there's a probability that I will sense an obstacle. There's a probability that I won't because my sensor is not all that good, right? But these are the influences that we have. Now, if we want to see this graphically, we can model it like this. Every state, right, t minus 1, t and t plus 1, and whatever state follows, is influenced, the arrows indicate influence, is influenced by my action at the time frame, and those influence the sensor output at that time. And the same thing happens, this state here is influenced by the previous state and by the actions that I took at that time step. And this state, whatever that state is, will influence what the sensors pick up. So now let's incorporate some measurements and controls in order to be able for a robot to at every time determine what's the probability of a given state of the world, okay? The way we're going to do this is like this. We're going to say that the beliefs of the robot, okay, have to do, are probabilistic, but have to do with whatever's been sensed and whatever the actions have been taken, okay? Now, the first thing that I'm going to do is I'm going to compute the probability of the change in state, okay, without the current sensor, and I'm going to call that belief bar of xt, okay? And that's going to be the probability of a given state, t in time slice t, with all the sensors except for the one in t, and all the actions including the one in t. So basically what I'm doing here, this is math lingo to say that my current state depends on the actions that I've taken previously and what I've sensed previously, but not what I'm sensing at time t, because what I'm sensing at time t actually depends on xt. It's the other way around. So, at every xt, okay, I'm going to do the following. There's going to be a little function called Bayes filter, and the input will be the previous state, whatever my action was at time t, and whatever the sensor input was at time t. And the algorithm goes like this. For all xt, okay, for all of the xt's, do the following. The belief without sensors of xt, so if I'm in a state and I took an action, the belief for my next state is going to be the summation of the probability of that state given that the action that was inputted here and given the state before that was given here, right, times the belief at xt minus 1. Now, how do I compute the belief at tx minus 1? Well, that's that's here, right? So it's recursive. So basically this belief will be the belief at xt minus 1. Now, the belief at xt, this is incorporating what I sense. So this is what I believe I just did with the state. And this is, well, let's look at the sensors and let's be more sure in my predictions, will be proportional to the probability of sensing whatever it is that I sensed, given what I believe about the state, times belief bar times what I believed without sensors. Okay? And then what I do is I return belief xt. So as you can see, this is a an algorithm that it's kind of recursive, right? So it can be done with dynamic programming, where I'm storing the beliefs and the beliefs bar at every, well, the belief bar I don't need, but I'm storing the beliefs at every given step to be able to use them in the calculation for the next xt, right? So this is how the algorithm of the Bayes filter works. Again, I give it a previous state, actions, and sensors at time step t, and then for all possible states xt, right, box in the middle, box up, whatever, for all possible configurations of the world, I compute belief without sensors, and then I apply the sensors to that belief. And once I'm done, I return that belief. So we're going to see a little example. For this, we need a bunch of tables. So let's assume a robot is looking at a door and needs to know whether the door is open or closed. The robot does not know whether the door is open or closed. It can only sense that. The robot has one sensor that can see whether the door is open or closed. It can be, a proximity sensor of some kind. xt is the state of the door at time t. So xt, my state of the world, will be, is the door open or closed at time t, right? That's all I care about the world. I don't care any obstacles, just is there a door open or closed at time t. This example was taken from Probabilistic Robots from Sebastian Thrun. At time t0, the robot does not know whether the door is open or closed. Okay, let's say that. So the robot will believe that there's a 50-50 chance that the door will be open or closed. That is, my belief at time 0 that the door is open will be 0.5. The belief that the door is closed will be also 0.5. Now, the robot sensors are not perfect. They're noisy. So let's assume that this is something that the sensor factory told us, or we've seen this, just by looking at the robot in practice. But if the sensor says open, when the door was open, that's a 60% chance. So there's a 60% probability that the sensor will say open when in fact the door is open. There's a 40% chance that the sensor will say closed when the door is open. So this is not a very good sensor, as you can tell. There's a 20% chance that the sensor will say open when the door is closed. And there's an 80% chance that the sensor will say closed when the door is closed. Okay? So that's what we know from the factory or from previous experiments with the same robot. Now let's assume the robot can push or do nothing with, it has an arm that can push or do nothing. That is, at time t, u sub t can be pushed or it can be nothing. Now, for example, if the robot pushes the door may or may not open, right? The robot might not have the strength to push the door, and we don't know if the door opened. So when pushed, there's a probability that the door will be open. For example, the probability that the door ends up open at time t, given that the robot pushed a door at time t and the door was closed before that, is written as follows, so you can understand the notation. What is the probability that the door will be open, given that I just pushed, and before I pushed, it was closed? That's going to give us a probability. Okay? Think about that. You can pause the video and think about it, but that's how we're going to note these things. So now, let's give a little example. So let's assume these are the probabilities of the door being open depending on the actions of the door. Let's say this is given, so you've observed this, and then you come up with these probabilities. So when the action is push, okay, if the door was open, the next state will be open with 100% probability. So if I push on an open door, the door will stay open, okay? That's basically pushing onto thin air because the door is open. Now, if the door was open and I push, obviously there's 0% chance that the door is going to be closed the next time step. Now, if the action is push and the door was closed, there's an 80% chance that I'll open the door. There are really heavy doors that I can't open with a push, and that means that if I push and the door was closed, it'll stay closed with 20% probability. If the door was open and I do nothing, it'll stay open 100% of the times, and it will be closed 0% of the times. If I do nothing and the door is closed, it will not be open. Actually, 100% of the times, it will stay closed. So I have these probabilities to play with. So now, these are what's called the transition probabilities. Okay, what makes me think that the state of the world is going to be in one state or another. I haven't looked at the sensor yet. Now, the question is, well, now as the robot stares into the door, what are its beliefs at time t, t+1, t+2? So basically the robot say it's approaching the door. What is it believing at each time step? Because as it approaches the door, the sensor might sense a little light, or it might be noisy for whatever reason. So the robot needs to compile this knowledge at every given time step, and then when it comes to the door, it has to make a decision. Does it push? Does it not push? Is the door open? Is it not open? It needs to know that, right? So at every time step, it's going to be sensing the door as it approaches it. In our example, it's just going to be looking at it statically. So the first step is to estimate what the robot's belief before processing the sensor data are. Okay? So at time step T1, the status of the door is X1. What the robot believes is denoted as belief bar of X1. So this is what the robot believes without sensing. Let's compute it. Let's assume the robot does nothing and the sensor reported that the door was open. Let's assume that that's the case. So the sensor reported the door was open and the robot does nothing the first time step. So we do the Bayes filter function and we'll replace T for 1, right? And then the robot does nothing, that's ut, right? And the door was open, that's xt minus 1, that's x0, right? So, belief at times of the world at time 1 will be the summation of all the xt possibilities, which are open or closed, the doors. What's the probability that the door now is open? I mean, what are the probabilities now if the door before was open, and what's my belief the door was open? And the same thing then with the door closed, and then I add those two values. So first, the first one. The probability of x1, given that I did nothing and the door was open, and my belief open, is x. Now I'm going to do the same thing for closed. Remember, I'm following the summation. So plus the probability of x1, given that I do nothing and the door was closed, and the belief that the door was closed. I will add these two. I have everything I need here. I have the belief of the door was open. We believe half and half, 50% chance that it was open at the beginning or closed, right? So that's going to be 0.5. And this, the probability of the next state, given that I did nothing and open, and with nothing and closed, I have from the table, from this table. Probability that this previous state is open and I push or did nothing, the next state is open and closed. So I'm going to be referring to this table. I'm not going to come back and forth from this table. Just if you need a minute, write it down. Pause the video now and write it down. Okay, so we're going to do the summation. I kind of told you where we're going to get these numbers, and they turn out to be the following. So this is going to be 1 times 0.5 plus 0.0.5, that's equal to 0.5 for open. And for closed, doing the same thing, we'll also get 0.5. So this is going to be our bell bar, belief bar. So we have the belief bar of open is 0.5 and belief bar of close is 0.5. This turned out to be the same as the initial beliefs. It makes sense. The robot hasn't done anything yet, right? So a robot believes the door is open or closed and it's doing nothing, right? Now, the next line in the program will compute the belief once the sensors have been sensed that the door is open, right? Which is this last line of the algorithm. Again, I'm referring, remember the table you copied? It might not be a bad idea to also, to also copy the algorithm here, copy that algorithm, and then copy the tables for the sensors. Okay, the probability that I sense something given the state of the door. So, let's continue. Now, the next line of the program, we compute this, right? So, the belief of x1, where this is some constant, and the probability that the sense is open given x1 times the belief of x1. And I'll do this for all values of x1. So again, the belief of x1 is a probability distribution, so we compute it for two cases, that x1 is open and that x1 is closed. Therefore, the belief bar of x1 has two possibilities, when x1 is open and when x1 is closed. So let's do belief of x1 open. I will do my normalization constant of the probability the sensor says open when the door was open times the belief bar of open, what I believe before the sensor sensed anything. And when it's closed, the probability that the sensor says open, and my belief is that the door is closed, and my belief before I sense anything is also closed. I do these computations. This I get from the table of sensors or from the series of probabilities for sensing. And this is because I already computed the belief bars 2 slides ago. I end up with 0.3 and 0.1 times the normalization constant for these probabilities. Now, because the belief of whatever the world is a probability distribution, its values sum up to 1. So this plus this has to be 1, right? So what happens then is that if we say this plus this equals 1, we end up with, if we solve that equation, we end up with eta being 1 over 0.4. That is our eta. And then we just plug it in back into these values, and we get the probability that x1 is open is 75%. The probability that it's closed, the belief that it's closed is 0.25. So now, look at what we did. We get a sensor now, right? That said open, right? The sensor says open on both. And now my beliefs change, and I believe a little bit more that it's open. But I haven't stopped fully believing that it could be closed. So I believe that x1 is open is now greater than the belief that x1 is open, right? Believe that it's now greater than the previous belief. I'm sorry, that's right. So I believe now that it's open more than I believed it before in the time slice before this. That is, after the sensor sensed open, the robot's belief that the door is open are even greater. So let's say that in T2, the robot takes the action push, and the sensor still says open for sensor 2. You can check that the belief that x2 is open, it's even greater now because we pushed and the sensor said open. So that door cannot be closing, right? And the belief that it's closed is really little. So as the robot, say, for example, approaches the door, it believes might go one way or another, and then it might take an action like retreat or push or whatever, right? For you, it is to do what happens now if the sensor says that the door is closed. That I leave that as an exercise to you.